Hi, we're going to talk about inverse functions. So inverse functions are, like their name, they're literally reversed, like backwards functions. So the best way I can express this is normal functions ask you and answer the question, if I give this input, what output do I get? And what an inverse function answers to is this question. To get this particular output, what input should I give? So the question is backwards. It's asking what input should I give? So the notation can be a bit confusing. So we're going to look at how they actually really work. So I have our old function fx equals 3x plus 1. Let's say that the output of fx is actually another variable called y. So y is our dependent variable and x is our independent variable. Okay, what is the input? It's x. The output is y. Right now, we haven't flipped the function yet. And so when I write it like this, it's like an equation. And y is expressed in terms of x. If I want to flip it, I'm going to reverse it. So what I'm going to do is try to express x in terms of y. So if I do that, I'll get 1 over to that side. And so if I divide the equation with 3 on both sides, this is what I get. And when I do this, I've expressed x in terms of y. So if I do that, we get this function, x equals 1/3 of y minus 1. And what I want is, okay, so what we want is an inverse function, right? And we actually have it right here. And this is our inverse function because I expressed it I flipped it over. So right now here, we have to say that the input is now y and the output is now x. But that's a little confusing because our input was x before. And so I'm going to just switch what was written here, switch the x and y. And okay, this is exactly what this is. This is the inverse function. So these two are the inverse functions. And here, x is the input and y is the output. That's why I switched this over. I can also, so instead of writing y equals 1/3 of x minus 1, I want to really say that this function is the inverse function of f. And so how I write that is f, and upwards here, I write a little -1. And that means this is the inverse function of f. So if I write f minus 1, x is 1/3 of x minus 1. That's the inverse function of this function f. Okay, let's think about this for a second. Think about it for a moment. So for fx, let's say I'm going to ask you this question. I want to get, let's say, I want to get the output of 1. So, okay, we have this machine f. Okay. Oh, sorry. Okay. So again, we have this machine f, and I want to get the output 1. What should I put it in as an input? So it's not obvious to me if I just have this and this picture. But say that we have the inverse function and we have it here right now, right here. And this is a new machine, an inverse function that answers this very question. To get this output, what do I need to insert as an input? So I evaluate the inverse function at 1, at x equals 1. So here, I'm going to evaluate the inverse function at 1. And if I do that, that's 1/3 of 1 minus 1, so that's 0. And what this tells us is that if I had 0 as an input to f, to this first function. If I had 0 as an input, so I'm going to write 0 here. If I had 0 as an input to this function, I would get 1. And so using the inverse function, I can answer the question that I had before. Hi, we're going to keep on talking about inverse functions. Now we're going to talk about it in terms of mappings and graphs. So here I have function f, fx equals 3x plus 1, and I have a mapping of that we saw before. And inverse functions are really easy for mappings. Okay, I'm going to try to draw the inverse function, the mapping of this inverse function. And so all I need to do, this was the input and this was the output, right? But for the inverse function, the output is now the input and the input is now the output. So all I need to do is to get rid of these arrows, and I'm going to reverse the direction, and we're going to try to draw the arrow. All I have to do is flip the arrow over, and that is the mapping for our inverse function. So our inverse function, if you put in 4, you get 1. Because for the original function f, if you put in 1, you get 4. So it's really easy for mappings. And for graphs, it's less easy, but there's a very interesting characteristic that I want to talk about with you. And so, okay, I'm going to use the same example. So remember that. We're going to go here. And so this is our original function fx. And let me also graph the inverse function that we calculated before. And so the red one is fx and the blue one is f minus 1x. So that's the inverse of f. And I'm also just going to draw y equals x here. Okay, let's look at this for a second. So that's just, this green line is just y equals x. It's a nice diagonal line, 45 degrees with the y-axis and the x-axis. It's going right, it's going this side. And okay, an interesting characteristic of inverse functions when you graph them, they are symmetric with the original graph, the original function, with respect to this diagonal line, y equals x. So if you look here, with respect to the green line, the red line and the blue line are symmetric to each other. So let's say I just didn't know what the blue line is. So that's our inverse function. I don't know what the inverse function would look like if I graphed it, but I have the original function and I have the y equals x function, the y equals x graph. All I need to do is flip this over with respect to the green line. And that is what our inverse function would look like if it were graphed on the same coordinates. And that's just not just true for this function. It's true for all functions that have an inverse function.